Good afternoon and welcome to the Music and Technology Seminar at Carnegie Mellon. Our guest today is John Kolar, recent graduate with a degree in Music and Technology from Carnegie Mellon. He was a frequent guest here in the Vlahakis recording studio, along with more than one band he formed with friends from the CMU Independent Musicians Organization. John is now a teaching professor at Ball State University in Muncie, Indiana, and a consultant in architectural acoustics for Polysonics. Today, John will talk about how sound behaves within indoor spaces. Please welcome John Kolar to the Music and Technology Seminar.
Thank you. Good to be here. How's it going? Hopefully good. I'm John. I graduated in May of 24, so 2 semesters ago from the CMU master's program in music and tech. So I was just there. I probably saw a lot of you, or we had classes together, but it's good to be back. So now I'm teaching at Ball State, like Ricardo said. So I'm here in Indiana. One of the classes that I got to teach this semester is a special topics class called Architectural Acoustics. So a lot of these slides would be related to that. And then from what I was teaching there, and then also I'm working part-time as an acoustics consultant as a remote job. So some of the work that I've been doing there, as well as some of the work that I was doing in my thesis at Carnegie Mellon, was related to the studio there and the acoustics of it. And then I'm also going to be continuing that work here. At some point this semester, Ricardo, I'll be back in the studio to do some measurements because I don't know if you all saw in the live room, there's new panels in there. So I did some measurements before those panels were put up, and then I'm going to do the after measurements and we'll compare them. So maybe once I do those, I can come back for another seminar and present the results or something like that. But yeah, so I'm John. Thanks for having me. Let's see here. So the acoustics of rooms and how they are perceived. This is a little overview of the presentation. Why is this topic important? Well, you can't trust your work if you can't hear it properly, no matter what you're working on. Taking the room out of the sound is a lot harder than putting it in. And no matter how great your gear is, it's doing a great job recording a lousy room. So these are 3 reasons that I came up with, and I'm sure there's many other reasons why this topic is important, but these are 3 reasons that I came up with for the importance. So we can talk about free field acoustics versus room acoustics. So in a free field, here's a picture of a speaker in the middle of the air, floating. The sound field is free of reflections. There's no walls or ceilings or other surfaces for the sound to reflect off of. Normally, this implies spherical radiation because a sphere has equal distances to the center on any point of its radius. So as sound emanates, it emanates in 3 dimensions outwards in a sphere. So this is sound propagation outside. Now we put a block around our room, right? And this is how sound reflects off of walls and ceilings. It would be spherical radiation, but until it encounters a surface. So this is like sound propagation inside. This lecture, we're not going to be talking about free field acoustics. We're going to be talking about room acoustics, so a speaker that has boundaries around it. So a little bit of the presentation overview. We'll talk about a brief history of architectural acoustics, sound encountering a surface, moving on to reverberation times, and then how we can use acoustic treatment to improve a room. We'll talk a little bit about room modes and then room acoustics effects, specifically on recording and mixing music. So a brief history of room acoustics. This example comes up a lot. It's an ancient Greek theater in Epidaurus. I don't know if I'm saying that right, but this is an ancient theater that still exists today. You can go visit it. It's a curved shape that created a natural echo chamber to amplify the sound. So the Greeks, I guess, noticed that sound on this hillside or on this mountain was acting specifically. So they actually built the seats naturally with the grain of the with the slope of the hill. So sound naturally propagates up the aisles and up the seats so that the acoustics make it easier to hear the performers in the circle on the stage. And then we also have some medieval Gothic churches So a lot of times, most people were outside or they were in small huts. But then we started to build big stone churches during medieval times with high ceiling stone walls that were very reverberant. And this was, very grand construction that had a lot of implications with God being there, right? So the church needed to be large because it was representing a higher power, and then also the music that was heard in there was unlike any music that would be heard in other places. So it's actually interesting. There are some acousticians who study, like they're ethnomusicologists, but they specifically study how the acoustics of the spaces of where music was being performed affected the actual performance and affected the composition. So, I mean, if you're working in an ensemble, you perform as an orchestra in a tiny practice room that's very dead and not very reverberant, you're probably going to naturally perform differently than when you're in a large concert hall. So it's also not only how it affects performance, but it affects the music that was composed in the era. And then fast forward to within the past 150 years, we have Wallace Sabine. I've also heard it pronounced Sabin, but I say Sabine. And he is deemed the father of architectural acoustics. So he was a young physicist at Harvard in the Boston area. And basically, because he was a young physicist, he didn't have much to do. He didn't have many tasks yet. So one of his bosses was like, oh, well, there's this lecture hall, this fog lecture hall that nobody likes. Nobody wants to be a student in there. Nobody wants to teach in it. And he went in there and was tasked with figuring out why it sounded so bad, and basically became obsessed with this to the point where he would go in there. The speaker hadn't been invented yet. The microphone hadn't been invented yet. All he had were his ears, some type of mechanism to make sound, and then a stopwatch. So he would go in there, produce a sound over and over again in different parts of the room, and he would try to figure out, okay, how much time is it taking for this sound to go away? And from all of his calculations, he developed a formula that became the first step in a scientific approach to architectural acoustics. We'll talk about his formula a little bit later on, but he was obsessive over this. He realized that, he couldn't do anything during the day because people were walking outside in the hallways, or the trains or vehicles were going by outside. So he had to do it in the middle of the night. And then he realized that the clothes he was wearing were affecting it. So then he would wear the exact same thing and go at like 2 or 3 in the morning to measure these acoustics. So it was all very regimented. And before him, there was no scientific approach to this. He eventually found a formula and was able to quantify sound in a room. He posed these 5 questions that I think are pretty interesting whenever he was doing his acoustics work. So one was, what are the quantifiable aspects of sound that are important for listening? 2, is a room that is excellent for speech also excellent for music, and vice versa? 3, how do the shape, size, and materials of a room affect the sound? 4, does sound die down at the same rate in different areas of the room? Does this depend on the sound source location? And 5, does everyone in a room hear the same things no matter where they're sitting? So these are all fairly simple questions, but they have elaborate answers, and he was working in an effort to answer these questions. So now let's talk about sound encountering a surface. We're talking about room acoustics, so sounds encounter a surface. So, simplified scenario, we have a sound wave that encounters one surface. We have 3 possible outcomes. We have reflection / diffusion, we have transmission, and we have absorption. So here's a little diagram here. We have an incoming wave at the top. The reflection would bounce back. The transmission would go through the wall, and you also notice that the through the wall is a dimmer color. It's not as bright because it would lose energy going through the wall. And then we have 3 as absorption. That's that red arrow there. So that's what happens when sound encounters the surface, and diffusion and reflection are grouped together because they're very similar. So let's break those down. Reflection itself, if we have an incident sound wave, it's incoming at an angle, it reflects at the same angle. So this is the exact same as light. If you have a mirror and a laser, you can point light at a mirror, and that reflected angle will be the same as the incident angle. So that's good to know. especially if we're trying to figure out how sound works in a room. And a lot of times when people are setting up their studios, they'll a lot of times put a laser on their speakers and then figure out where their reflections are going to be by placing a mirror on the wall, to just kind of get a better idea, a visual idea of how sound will reflect in their room. So that's convenient that light and sound act the same way in that sense. So that's the reflection. And then we have a special type of reflection called diffusion. So when sound encounters a rough surface, it will spray in various directions, and that's a function of the frequency or wavelength of the sound, and then the size of the bumps on the wall. So the sound does not reflect at the same angle. So the first one on the left, we have reflection, and our blue arrow is basically just as bold and big as the orange because it hasn't lost as much energy. Now with diffusion, we have multiple reflections, and then that arrow gets smaller, so it loses energy because it's getting dispersed in a lot of different directions. So that's what diffusion is. And then we have transmission. So sound travels through walls and surfaces. If you have an annoying neighbor, I'm sure you know this, right? Someone upstairs is banging on the floor, or they're listening to loud music, and then you hear whatever they're listening to. So sound travels through walls and surfaces, and we have in the acoustics consulting world a something called STC, which is the sound transmission class. So basically, it's a rating that says how well a wall or a partition will isolate sound from one room to the next. So a higher STC means that it's going to be better at isolating the sound. So you can see in this example, we have room 1 and room 2 in the blue, and basically the sound on the left is big, and then it travels through, and it is smaller, but still a little bit bigger than the example on the right, where we have room 1, which is orange/red, and room 1 to 2 on the right has a higher STC, so the sound gets more absorbed. And if you notice, the main difference is that here we have, I don't know if you can see my cursor or not, but here we have a wall on the left and then another wall on the right. But then on the second scenario, we have 2 walls on the left and then 2 walls on the right. So the increase in mass, which is basically would just be 1 layer of drywall versus 2 layers of drywall, that increase in mass will absorb more sound and will prevent transmission. Okay, so the one on the right would have a higher STC. And then we can talk about absorption. So sound has energy, and absorption is caused by the sound's energy being transferred to heat when it encounters a surface. So if your heater is broken, I guess you can just scream, and then you could be able to heat up your space. Continuously scream, I think, is the answer. So there it is, sound hitting a wall and getting dissipated as heat. So here's a question for you. How long would it take an 80 decibel sound, this is dBSPL, and a hairdryer that's probably about a meter from your face, how long would it take for just that sound to heat up an 8-ounce cup of coffee to like normal coffee drinking temperature? Any ideas on how long that might take?
Maybe like 12 hours.
12 hours? Solid guess.
12 years.
Any other guesses? And I don't know if I can see the chat, but if there's one in the chat, let me know. 12 hours, that's pretty good.
A couple of days.
What's that? Should be a very long time because water has high specific heat. That's true. That's true. Very long. Approximately 1.5 years.
1.5 years. Damn.
So you can just scream into your coffee cup for 1.5 years, and then you can drink it. Yeah, I wonder how it would work with a different liquid, right? Good point. So yeah, it takes a long time. So basically, it's dissipated as heat, but it's negligible. Cool. Moving on. Let's see here. Now we have this thing called an absorption coefficient. So it's a spectrum of 0 to 1, where 0 is absolutely no absorption and 1 is complete absorption. So 0 or closer to 0 on this spectrum would be something like glass, drywall, brick. And then closer to 1 on the spectrum would be an open window. So an open window is completely absorptive. No sound is going to bounce back, be reflected back. Okay, so we have a lot of different materials, and there's this absorption coefficient that we can use to dictate how absorptive it is. There are some absorption coefficients, maybe we'll see here. Yeah, here are some examples. We don't have any here, but sometimes they go greater than 1, and I don't know how it works. It might just be a marketing scheme for these people who are developing these materials because they want you to absorb more than 100% of the sound that's playing in there. But here's some common absorption coefficients. We have brick. The first thing I noticed about brick, which is super interesting. Let's see. No, maybe it's not on the brick. Let's see. It's better on this one, the concrete block. So it's the same concrete. It's the same material. It's light and it's porous. And we have 30% of the sound is being absorbed at 500 hertz. We have about 30% at 1,000 and about 40% at 2,000. But then you paint it and it goes way down. So it's not just the material itself, it's also the porosity of the material. So if that paint gets in there and fills in the holes, then the sound cannot fill those holes and the paint is clogging them up. So now we have a much more reflective surface because of the paint. So there are different companies out there who are developing acoustic paint that is supposed to not clog pores like this and keep the porosity of the material consistent. But yeah, it's interesting that paint will affect it that much. And there's just some other materials here. We have wood, ordinary window glass, and a lot of times these coefficients are a little bit more granular with the frequencies that exist. So they're normally in octave bands, and you can get even more specific into third octave bands as well. But we use this a lot in our work to figure out reverberation times. So the coefficient depends on the characteristics of the material. We got the density and the porosity, among other things. So that's why the paint affects it. So then what happens when we introduce multiple surfaces? That's what happens when we have a room. So sound travels along a direct path straight to the listener. Sound travels also along an indirect path where it's reflected off of walls, floors, ceiling, any surface. And the direct path arrives before the indirect path. The speed of sound is constant. It's traveling a shorter distance, so it's going to get there sooner. So here we go. We have our performer on the stage. The direct sound is getting to the audience member sooner than the reverberated sound. Then there's something called the precedence effect, right? So if two versions of the same sound are heard, separated by a sufficiently short time delay, a single auditory event is perceived, and sound is localized to the source of the direct sound, right? So as long as our direct sound is coming not that much sooner than the reverberated sound, we hear that as an overall reverberation and not as an echo. And that reverberation is a characteristic, kind of like a thumbprint of the room, as I'm sure all of you know because you've been human beings and experienced different rooms. So how can we quantify room's acoustics? One main way that we do so is through RTs, reverberation times. So that's the amount of time it takes for a sound to dissipate within a room. We specifically use an RT time called an RT60 that is very common in the field of acoustics. And that's the amount of time it takes for a sound to dissipate by 60 dB SPO. So RTs are specific to a given room. They're kind of like their thumbprint. They're based on several factors, the dimensions and the materials on the walls, floors, and ceilings. So how is it determined? If I wanted to figure out the RT for my specific room, there's a few ways you can do it. Normally, it's done using a broadband signal of all audible frequencies with a short duration. So you do a frequency sweep of sine waves or a balloon pop or a blank gunshot. And then the sound and its decay are recorded with a high fidelity measurement microphone, normally with as flat of a frequency response as possible. If it's not as flat, even if it is as flat as possible, that's still accounted for in the calibration of the measurement. And we get a reverberation time. So here's a graph. We have dB on the y-axis versus time on the x-axis. We have our direct sound, which is our first reflection, and then we have an initial time delay, or an initial time gap. So this would be determined by the space between our first reflection, between our first sound and the first reflection, or the distance between where our source is and the first surface. So we can figure that out. If we know the speed of sound, we can figure out the distance, right? So that first reflection is going to be the loudest compared to all the other reflections because it hasn't had as much time or distance to dissipate, and it hasn't been absorbed by a surface. So that's the first reflection, and then we have early reflections which then dissipate down to the reverberation, which goes down to the 60 dB. We measure how long it takes to go down 60 decibels, and that is our RT60 time. So this is completed with, if we're doing it in one room, we'll complete it with different loudspeaker locations. So our source will be in different locations. I guess if we're using a balloon, we would use multiple balloons in multiple spots around the room, and then we would average them, and we would not place a loudspeaker close to a wall. We would want it to be further from the wall so that we have a larger initial time delay gap. And then we can average all of those together to get a better holistic understanding of the room's RT. So this is a measurement example. This is from my thesis from spring semester, and I was working in the SXL. It's the spatial computing lab in Margaret Morrison. And we had a wavefield synthesis speaker array set up, which you can see right there. Rectangular room, concrete floors, high ceilings, long RT, a lot of noise, old radiator in there, unideal room acoustics, right? And then the room that some of you were sitting in, I went in there and I measured the room acoustics of that room. That's a picture of what it looked like when I had that wavefield synthesis loudspeaker array in there. So it's highly controlled acoustics. We have absorption and diffusion, short RT time, low background noise, and more ideal room acoustics. So I compared the two of them. And in the red, we have the SXL versus the control room. And here we have the RT times. So we can see here, just by reading this graph, this is 0 dB. This is minus 60 for the control room. It looks like it was about, 150 to 200 milliseconds. For the spatial computing lab, it was almost to 700 milliseconds. So that's the difference there. And then what's nice about this, I use Room EQ Wizard, which is a great software and free if you're interested in doing this. It also breaks down your RT60s in terms of frequency. So here we have the RT times versus frequency, and we have the SXL in red and the control room in blue. So you can see all of the RT60 times depending on their frequencies. So it's hard, even though the control room is pretty controlled frequency-wise, it's hard to control those lows. And then they taper off in the mids, and there's pretty steady from 200 on. And then in the SXL, it's just kind of crazy, and then the high frequencies are absorbed. So the RT60 values are different for different frequencies. So here's some common RT times. You know what they sound like, but you maybe didn't know exactly how long it takes for sound to dissipate 60 decibels in these rooms. So voiceover, they like to be under a half a second. A control room is 0.3 to 0.5, which I think is what we had here. If we look, control room, yep, we're looking at even better. It was 200, right? So control room 0.3 to 0.5, that's even better acoustics than what this general recommendation is. Tracking room is a little bit more live. That's half to 0.5 to 0.8. Typical living room with all the furniture and the size and the carpet normally is a half of a second. Typical classroom is a second. Concert hall and church with organ go up to almost 2.5. So that's for desired reverb times in seconds with RT60s. And this is also not frequency dependent. So this is probably at 500 hertz. That's a normal standard. If you just see an RT60 time, I'm pretty sure most of them without specifying are at 500. So if we know the speed of sound, which is 1125 feet per second, we can multiply that by, for instance, a half a second, and we can figure out how far the sound is traveling before it decays by 60 dB. So in this specific case, for the control room, if it was a half a second, it would travel 562 feet. So here are the distance traveled in feet. That's another way to look at it. Instead of thinking about how many seconds it takes, you can think about how far it has traveled before it dissipates by 60 dB. So if you look at the church with an organ, it's traveling like almost a half of a mile before it dissipates 60 decibels. So sound travels pretty fast. Cool. This is Sabine, the guy that I mentioned before. This is his equation. So the TRT60 is the reverberation time, and we can set that equal to some constant times VM, which would be the metric volume of the room. And then that's all divided by S, which is the total surface area. And then A with a hat would be the absorption of those surfaces. And then depending on your cubic feet or cubic meters, you can change that constant. So it's only a function of volume, surface area, and absorption. And the Sabine equation is pretty good. It works well. There are some other equations that are used depending on the application. So concert halls have a different equation. And I think classrooms have a different equation. So there's general recommendations. So a lot of the work that I do as an acoustics consultant is doing RT60 calculations. So a lot of the times we will get a client will reach out to us, an architect, and they will say, we want to build this new school. Well, we do a lot of schools. So what I'm about to show you is from middle school. And they'll either be renovating the school or they will be doing a new construction. So I don't have the liberty to go, and I don't have the ability to go into these schools because they aren't built yet. I can't go into them and measure their reverberation times. So I have to look at the architectural drawings and figure out the dimensions of each room, the surface area, the volume, and guess at the absorption based on the materials that they have so that we can figure, okay, this is going to be the reverberation time of this room. Is that too high for a classroom? Because if it is too high for a classroom, then the lecturer is going to get drowned out by the reverberation and then the students won't be able to understand them. So it's important for the clarity of a classroom, similar for a gymnasium or an auditorium or a cafeteria. All of these places that exist in a school, they need to have a reverberation time below a certain threshold so that they can be functional. So here's an example of some of the diagrams that I would be looking at on a normal day doing the RT calc. So these are all of the different types of doors that might exist in this school. We have a scale here, 1/2 of an inch equals 1 foot. So I can measure the dimensions of this door and then also exactly what's going on with the framing of the door. And then normally the material would be listed here for wood, for instance, and that would have the specific absorption coefficients. This is a plan view. So this is like a top-down bird's eye view of different classrooms. So here we have the room number. This would be a classroom grade 6, and then 863 SF for square footage. And then basically I can go into a PDF viewer on steroids and measure these. So I can confirm that this square footage, I can measure the length of these walls. I can subtract out the length of this door here. And then this is also window down here. So I can change the materials of the walls. Normally we have gypsum wall board, which is drywall on the walls, and then this is glass for the windows, and then normally a wood door. The ceiling tile would normally be an acoustic ceiling tile. The floor is normally some type of like composite vinyl tile. So all of those would have absorption coefficients split up depending on the octave. And we can look at that. And then also, if I want to figure out how big the windows are, I can look at it from an elevation zone. So now we're standing outside of the school, looking at the school, and I can take this same measurement scale, measure the size of the window, and now I know how big my windows are because the windows aren't normally floor to ceiling. And then we can also see how high the roof is, and we can figure that out. And then we have something called a finish schedule. So this is basically what the flooring would be, what the base would be below the flooring, what the walls would be, what the ceilings would be. So CFT, there's a lot of abbreviations: ceramic floor tile, carpet tile, a lot of different materials, and then the manufacturer, same thing with the base. The walls, we have paint, which is normally just on gypsum on the drywall, and then acoustic ceiling tile that are all based on these manufacturers. And then normally within a big set, because there's like multiple PDFs, hundreds of PDFs for all of the different drawings for a given school, they will have this kind of like general room finish. So here you can see every classroom, for instance, will have VCT, which is a composite tile on the floor with a rubber base below it. The walls will be painted, and then the ceiling will be this acoustic ceiling tile. So you can kind of look at this on a general form and see all of these. We type everything into a spreadsheet. We have a master spreadsheet of all kinds of materials, all their absorption coefficients, and we can just, it's coded so that it will spit out the volumes and the surface areas and do the proper subtractions to take the surface area of the door out of the surface area of the wall and that type of thing. So we just have this master spreadsheet. We type everything in, and then basically the spreadsheet will tell us if the reverberation time at a specific frequency is exceeding a threshold that is given for, say, a classroom or an auditorium. So it's cool work, and it's honestly pretty straightforward. If you can find the volume of a room or find the surface area of a room, and you can use Excel, you can do it. So I imagine a fifth grader could do it, but it does also require a basic understanding of sound and how it will travel through a room. But there's a lot of jobs in this industry too, and I think it's with my music and tech, I did an internship the summer between my first and second year of the master's. So definitely with your education at CMU, you'd be qualified to join this industry. And there's acoustics consultants everywhere. As long as new buildings are getting built, acoustics consultants will be being hired. So, and there's a company in Pittsburgh too that did the recording studio. They just changed names. I think Ricardo remembers the name. I don't, but there's industries for sure. And then, so we have a room, and let's say that it's bad. Say that we don't like the reverberation time there. How can we treat it? So we can use a combination of absorption and diffusion. So, if you're in the studio, you can see the diffusion on the back wall, which is basically, it looks pretty similar to this. And then the absorption is, I guess, behind those wooden panels on the sides. So combination of absorption and diffusion you can see in the studio. And when do the reflections become a problem? They can cause comb filtering. So we get this filtering issue that will cut out certain frequencies and boost other ones. So we don't want that to happen because we want as flat of a response as possible, especially in a critical listening environment. So we want to control these reflections so that we can mitigate the effects of comb filtering. Okay, so here is absorption in a mixing room. We want to control the first reflections from the speakers. If you remember from the diagrams before, those first reflections are the loudest ones. So if we can tame the loudest ones, we can do a lot of good there. So here we have these speakers. And if we had a laser on this speaker coming out here, this would be the first reflection to the ear. And then this would be the second reflection to the ear. This would be the second reflection to the ear, right? So if we put an acoustic panel right here and it will absorb that sound, we can tame those first reflections. There will also be first reflections on the floor and first reflections on the ceiling as well, if you picture this in 3 dimensions. So we put absorption panels at these first reflections on the side, on the front, and on the ceiling, and the absorption will reduce the RT time. And then we can put diffusion in the mixing room. So diffusion is often found at the back wall. It sprays the back wall reflections in various directions. They lose their energy and don't distract from the direct sound from the speakers. This won't reduce the RT time because it's not absorbing it, it's just reflecting it. It will reduce it a little bit because there will be inherently absorption, but not as much as the actual absorption. And maybe you don't have a budget for a high quality acoustic diffusion panel that you would hire a consultant for or make. You can just use a bookshelf. So if you put a bookshelf behind your speakers, normally people don't have all of the exact same size books, and they have a combination of hardback and softback. So this is a great acoustic diffuser, and you probably already have one. Low frequencies are troublesome. So normally, if you're buying acoustic panels that are absorptive, they're only going to guarantee good absorption from 500 up. You'll be lucky if it goes any lower. So absorption and diffusion can really only control mid to high frequencies. The low frequencies will require bass traps that look like this, or Helmholtz resonators. And Helmholtz resonators are kind of like a glass bottle. If you blow over the top, it'll whistle at a certain frequency depending on how big the bottle is. So you can tune a resonator to be at the frequency that is troublesome in your room, and then that will capture the sound at the troublesome frequency and will absorb it, and then it will mitigate its negative effects. So that's how we can treat the room. Another thing to consider is that rooms are resonance spaces. What is resonance? I've seen a lot of different examples of definitions. I liked these two for this presentation. The natural frequency of a system where it oscillates at its greatest amplitude. Also, when talking about sound, it's the sound which is produced by an object when it vibrates at the same rate as the sound waves from another object. So that would be a sympathetic resonance. If you've dealt with a tuning fork before, if tuning fork A will resonate, tuning fork B will often resonate next to it as a sympathetic resonance. So there's different definitions for resonance, but I like the first one when we're talking about rooms, a natural frequency of a system where it oscillates at its greatest amplitude. So depending on the size of the room, based on the properties of it, the length, the width, the height, the shape, whether it's rectangular or spherical, and then the materials of the room, certain frequencies will resonate more. And there's most of the rooms that we live in tend to be rectangular, so they can be easier to calculate with just length times width times height. Normally, though, in studios, parallel walls are not your friend. So in that studio specifically, you can see like the glass from the control room into the studio. That glass is not parallel. There's two glass panels and they aren't parallel. So that reduces the standing waves there. Yeah, and just next time you're in a good recording space, take a look and see if the walls are parallel. That the parallel walls can have a lot of buildup of standing waves, which creates a flutter echo, which is not a desirable sound. So if you make them not parallel, then you'll reduce that effect. There's several cool shapes, like an ellipse here. I don't know if this YouTube will work or not. But either way, I'll send, yeah, it doesn't want to work. I'll send out these slides too, and you can look. But basically, it's an animation of an ellipse. So if you stand at one focus point of an ellipse and you talk, and then another person stands at the other focus point of an ellipse, you'll hear them as clear as day, because all of the reflections coming off of this one will bounce back and hit there. So there's some saying that like one of the founding fathers knew about this and realized that the Capitol building was designed as an ellipse in the Senate, and he put his desk exactly on this side, and they would split, one political party on one side, the other political party on the other, and he knew exactly what they were talking about the whole time. And they thought that he could just hear that he knew the future, but really he just knew about acoustics and could hear exactly what his opponents were talking about. So yeah, I guess it can be useful if you don't tell your friends. You can hear what they're saying about you. So that's a cool one, but most rooms that we're in are not ellipses. So we can have these room modes that are collections of resonances in a room based on the geometry. So these are pretty easy to figure out. It's basically if you figure out what the wavelengths are of the frequencies that would exist at similar dimensions to your room. Basically, it's a ratio of the wavelengths of the sound to the dimensions of the room, and they're both measured distances. So you can just compare those two. And these room modes will determine how loud a sound is in your room. So here we can use the speed of sound to calculate the resonant frequencies of the room based off those dimensions. And here's an example of those resonances. So if we have these as our sidewalls with a distance of 21 feet, this would be one full wavelength of 27 hertz. This would be two full wavelengths of 54 hertz, three full wavelengths of 81. And we can see how that might affect the sound in this little diagram here. So the square, or the little red dot, the square represents the room, right? And the red dot is a loudspeaker playing one resonant frequency. So as you move the loudspeaker through the room in changing its position, this amplitude line right here will change. So when the loudspeaker is in the middle of the room, what do we get? We get complete silence because this loudspeaker is radiating sound to this wall and to this wall at the same time. They're reflecting back and they're going to be 100% out of phase with each other and they're going to cancel. So this wave is the output here of the sound as the loudspeaker moves through this room at a specific resonance. And it's just crazy that there is a point with total silence. So what's going on is this destructive interference. We have one wave that's 180 degrees out of phase of another, and they are summing to silence. So it's important to consider the acoustics in your recording room, like your mixing room, because you want to consider these reflections in these room modes. You don't want to put a mic in a spot that is a null of a room mode because you're going to filter out that specific frequency. You also don't want to place your performer at a null of a room mode. It also depends on the instrument, because if you have an instrument that produces frequencies that are especially important and they overlap with the room modes, you just want to consider all of these things. And we want to avoid comb filtering and destructive interference. So it's important to consider these things in the recording room and then also in the mixing room. And here is one example. This is fairly related. It's still with the phasing and the comb filtering aspect. But, if we're recording a drum kit, normally you want your overhead mics equidistant from an invisible line that cuts through the center of the kit. Because if your overhead mics are not from the same distance of the snare, then the sound's going to arrive at different times and in different phases. And then whenever you sum them together to listen back, there will be comb filtering. So just like the distance between your mics, you also want those mics to be placed in a spot in the room where they're not at those nulls in the resonances of the room modes. And to wrap up, basically, it's important to consider both the reflections and the room modes when recording, when listening to playback, when mixing. An acoustic treatment does not need to be excessive to be effective. Like we saw, if we tame the first reflections, that's going to be more advantageous than just throwing in an acoustic panel anywhere on the wall. So correct placement of the treatment for a specific room will do a lot of good. So we can revisit Sabine's questions from the beginning. What are the quantifiable aspects of sound that are important for listening? The one we mentioned today is RT times. There are others. 2, is a room that is excellent for speech, also excellent for music and vice versa. We didn't necessarily touch on that a bunch in this presentation, but not necessarily, right? Music has different frequencies that are going on compared to speech. Speech has an intelligibility aspect that music doesn't necessarily have. We don't need to understand exactly what the violin is saying. We can just listen to it and enjoy it, unlike a lecturer. 3, how do the shape, size, and materials of a room affect the sound? They affect the reverberance. As absorptivity increases, the reverberance will decrease. As the room size increases, reverberance will increase, and that will also affect the clarity of the sound. Does sound die down at the same rate in different areas of the room? Does this depend on the sound source location, right? So we saw that the sound is going to be different in different parts of the room depending on the room modes, right? And there's even a point where we can see that there's nothing going on. Does this depend on the sound source location? Yes, as we saw in the room modes diagram. And 5, does everyone in a room hear the same things no matter where they're sitting? No, because the reflections are louder near walls and ceilings. And also we saw the room mode aspect as well. And that's it. Opening it up to questions now in the last few minutes. Thanks for having me.
I have a question. This is
Sure.
Leon. You mentioned in the reverberation time high fidelity microphone.
Right.
What do you consider brand or whatever high fidelity microphone?
For sure. There are definitely like brands that sell specific acoustic measurement microphones that you can look at. They definitely aren't cheap a lot of times, but most of the time they're looking at a small diaphragm condenser microphone. Condenser microphones have a relatively flatter response compared to dynamic microphones. But I think in the end, depending on your application, as long as you're properly calibrating your microphone to incorporate that into your measurements, the microphone just needs to be capturing all frequencies.
You
as
don't
long-
want to be specific on one or two?
I'd have to do a little bit of research to figure out. I'm trying to remember exactly which ones we used at work, but
Okay,
I'll look at my documentation. I'll send it to you.
okay. Ricardo will probably tell you they're Sheps.
Sheps, yeah, right. Those are great. Yeah.
Thank
For
you.
sure. Yeah, I'll send you a few.
Thanks.
Yep. Any other questions or comments?
Yeah, come on.
I'll ask another one. What do you deal with the, in my home studio, I have, it's up on the second floor and it has roof lines. So
Mhm.
how do you deal in those equations with angles?
With angles, right. So normally those equations are a
Is that
lot
a mirror? You get a mirror or something?
right. So those equations are a lot easier to deal with when they're boxes, right?
Yeah.
We could still calculate the volume of that room. We would just have to do a triangle and then
Right.
a square. But yeah, the reflections themselves, we would probably want to measure the angles. And at that point, I didn't mention it here, but there are a lot of acoustic simulation softwares where they're compatible with a 3D model of the building. You throw that in, and then you can run a simulation of sound in them. So a lot of simulation softwares exist to do that. So that would probably be a good bet. We could easily mark up, depending on the angles of your building, put that into a 3D modeler, and then run it through a simulation and see what the deal is.
I have a question.
Yeah.
So, I'm just asking, like, I'm wondering how you got into like getting interested into like these acoustic, architectural acoustic sounds, I guess.
Definitely. Yeah, I mean, I was that internship that I did, it was at a company called Arup. They really like guided me through learning how the industry works and learning how to every aspect that goes into it, which was great. Before that, I just had my hands on a few books. I took Tom's electroacoustics class, which touched on room acoustics a little bit, but that was a great class and you should take it. But it didn't touch on room acoustics enough, Tom. I don't know if you it's an electroacoustics class, so it shouldn't. Uh, but yeah, I was just automatically curious, and I bought this textbook right here. Maybe it's not gonna. It's just called Architectural Acoustics. It's by Marshall Long, and this is like the Bible. When I did the internship, this was on everybody's desk, and they were constantly referring to it. So it's like it's like $100 textbook. It's not super cheap, but like it's the one, and it's goes in depth on a lot of things. So I think just from reading and taking as many acoustics classes as I could get my hands on, but it's related to the ECE stuff as well, because if you're studying the wave equation for electromagnetics or you're in a physics class for optics or whatever, anytime you see the wave equation, it's relatable to the acoustics stuff. So
The author's name was Marshall what?
Long,
L-O-N-G.
LONG. Yeah.
Okay.
Yeah, the architecture department used to have an acoustics course years ago, but I don't think anyone over there is teaching it right now.
Yeah. Yeah, and I think that, there's definitely an industry need for it, because spaces as they're getting built, they need to sound good. So, but
Is there no magic box you can use in a simple environment? Just throw
Any
it in there and get some answers?
yeah, there are some, speaker tuning systems and other things that if you have a higher end system in your living room, there's some tuning tools to use. Magic box though, I don't know. I'll look.
All right, I'll give you some time.
I'm curious, could you speak to, or do you work with, or can you speak to how these principles apply in situations where the space has other demands that are maybe contrary to the needs of excellent acoustics, such as like theaters with dynamic sets, or
Right.
sound stages, opera halls, that kind of stuff.
Right. Well, and that's another thing too when we're working, right? Because we are just the acousticians. We're dealing with the electrical team, the mechanical team, the lighting team, the structural team, and the architects themselves. And most of the time, the acoustics are not valued in that grand scheme of things, right? Because you need heat in your system. You need heat in your building. You need lights in your building. Now, people don't think about the sound as much until they get into the space and it's already built. But yes, with dynamic things, it's definitely a challenge. One thing that I like, though, is that a lot of products are starting to combine, for instance, insulation aspects. So I think probably several years ago, insulation was just rated for how much heat it would keep in or not transfer, right? But now you'll see a lot of insulation rating its acoustic properties as well. Because if I'm plugging a hole in my around my door in my door frame, that's also helping. It's helping to keep my heat in my house, but it's also helping to keep sound from outside from coming into the house. So I think that there are a lot of moves towards kind of combining the product development of insulation, heat, or of insulation and acoustics and other ways. But specifically in a concert hall that has changing sets and everything, like that's definitely something I haven't dealt with personally in my work, but it's an interesting problem to solve, and it's right, because the set's going to alter the sound on your stage, right? So yeah, that's a great point. I don't have any specific answer for you, unfortunately, but
John, I have two questions for you.
sure.
Are acoustics of large spaces different from acoustics of small spaces?
Right. I would say yes, right? As the space increases in size, the reverberation time is going to increase. And, we perceive sound as one auditory event if the reflected sound is close to the direct sound in time, right? But if you go to the Grand Canyon and you speak, you're going to hear an echo, right? You're going to hear your echo talking to yourself. So obviously there's a perception aspect too, that once the room gets so big, it becomes disorienting to the point where I'm hearing a lot of things. So there's a psychoacoustic aspect to how we perceive large spaces versus small. Also, people in anechoic chambers, that's a small space without reflections, they'll hyperventilate or they'll feel claustrophobic even though the walls are they're in a normal sized room, right? So I think there's definitely a human aspect to understanding how big the room is based on our sense of sound. That's definitely affecting our perception, but the physics of it doesn't necessarily change that much. The equations are the same depending on the size of the room for the most part.
My second question is more involved, I guess. Do you know anything about the history of the acoustics of the concert hall that the New York Philharmonic plays in?
Is that the one that had all kinds of issues over the years and was constantly renovated?
Sure is.
Yeah. So I've been keeping up with it just to read it because it's a funny, maybe it won't not isn't the best word, but it's an interesting use case in the world, because we don't want, as acoustics consultants, we don't want that to happen to us, right? I don't know much about it, though, the specifics of why it wasn't liked. I should read back up on it, but I have definitely heard of it.
Yeah, there was an article in the New Yorker magazine many years ago about the first big renovation that they did in that hall.
Yeah.
The recommendation as soon as they built it, they knew that it wasn't right.
Yeah.
And, so much research has been done for reflective surfaces and absorptive size of the shape of the room. All of this stuff has been done, so everybody knows what it should be if they only follow the, follow the rules that everyone has.
The guidelines, right? Exactly.
So, yeah, Rich knows about this because Bose at MIT used to use this as a case study in his acoustics class all the time.
It wasn't. I've been trying to chime in, and it seems like the microphone wasn't running. And this is a very famous case. Can you hear me now? Anybody?
Yes.
Okay, great. So the acoustic designer of the original Philharmonic Hall was Leo Brannick. And you all know him as the first B in Bolt Brannick, and actually the second B, Bolt Brannick and Newman, now BBN, now something else. But also, of course, the author of the textbook that many of us used either directly or indirectly in our acoustics courses. And he was a big fan of lots of acoustic measurements, was very well known very cherished member of the Acoustic Society and a former president, died at more than 100 years not too long ago. I've shaken his hand once or twice. But there was a big book out that was published in the mid-60s, which you would enjoy looking at, in which he measures concert halls all around the world and comes up with a design specs for the ideal concert hall, and then talks about how it's going to be implemented in the new Philharmonic Hall coming up. And at the end, there's a photograph of Jackie Kennedy and Leonard Bernstein sitting together and smiling at each other in the new Philharmonic Hall. And indeed, when the hall opened, it was a disaster. There's an article in the Acoustical Society, which you can find pretty easily by Beranek. The title, I remember, was The Changing Role of the Expert. And what he describes in the article, of course, is written by him, was that he did all this work, but then the architects came in, and the last thing the architects cared about were acoustics. They're just interested in the vision. This is even for an important auditorium like this one. And it was claimed that they didn't pay any attention to him. And then when things went south, they brought in somebody else, and I forget who the somebody else was, but and he doesn't cite it, but the New Yorker article certainly does. I think it was Harris, one of the other big firms. And Harris and Beranek, shall we say, were not friends and hadn't been from some time before then. And Harris had no vested interest in having Beranek look good. So the real problem with all of those is that all of those theories, and I'm a big fan of Sabine, don't get me wrong. When I used to teach the same electroacoustics course, and indeed picked up on it the same way Tom did. We were both students of the version that Elmore Bose taught at MIT many years ago. It was the Sabine equation was really great in theory, but again, it's critically dependent on just being a statistical model of the room. And there's so much going on in real rooms that your mileage is going to vary. And generally, going into the real room and making actual measurements is almost the only way to fly. Certainly, Bose Corp has gone to a great deal of effort to, and so had BBN, to model concert halls. But typically what they do is they build miniature models of the concert hall rather, with the appropriate fabric and drapery and everything like that, scaled down, and then they run things at a frequency, scaled up accordingly, so that the relationship between the size and the wavelengths is what it would be. But it's just a very, very inexact science, and we all kind of revel in these spectacular failures. Like the Tacoma Narrow Bridge that fell down, which you'll see in, everybody's undergraduate physics class. And Tom, you have anything to add to that? I do, by the way, I do recommend the New Yorker article. Okay. Look for, search within the New Yorker website for Beranek or for Avery Fisher Hall. Or, and it was, I don't know. I do remember the last time the last years when I used to teach the electroacoustics course, I would spend a day or at least a half a day talking about that whole incident and bring in the article by Beranek and read from it, and the same thing from the New Yorker, and they're great sources for answering the question. But they've even redone that fairly recently, so it's there's a fundamental problem. I think it has to do with the room being too large or too wide, competition between what you need to do to have the space be financially viable and what you need to do to have it work acoustically according to what people believe are the principles. Anyway, I won't have too much airtime, but that's what I can add to the discussion.
Great, thank you.
Hey, John, I have one more question. I have a plug-in with a group from Amsterdam called Altiverb, where they use this convolution reverb.
Yeah.
Where they, put a microphone in seat 17, owl, whatever.
Yeah, right.
Do you familiar with that? And do you have confidence in, because they supposedly are creating, if you have a good place, can you take a recording throw that in and get something similar?
Definitely. Yeah, the guys who you want to talk to about that are Ricardo, Tom, and Rich. But yeah, Ricardo uses it all the time when he's mixing. Like I remember in the classes, there's a waves convolution reverb that we used a lot, and Ricardo has a few theaters that he likes. It was like specific seats, but yeah, the processing behind it is great. They also use that similar method for guitar amps. So if you want a guitar amp simulation, they'll get an impulse response measurement of guitar amp,
Yeah.
and then
Okay.
you can run that. So it's used in multiple aspects of signal processing, and it's
So you have confidence in it?
definitely, yeah.
I didn't know Ricardo used it. He never told me that.
Yeah, definitely. Yeah, he does, and there's a few like opera houses and concert halls that are saved as presets in the plugin. Ricardo used a different one. It's the Waves version, but it's the same idea.
Okay.
Yeah.
Great. Thanks.
Yeah, of course.
Are there any other questions?
I've got an interesting comment. We're talking about the New York. I haven't been to the New York Phil Concert Hall, unfortunately, so I can't speak to that. But I had an interesting experience about a year and a half ago at the Walt Disney Concert Hall. I was going to see the LA Phil, and being a starving artist of sorts, and also operating the principle that a lot of concert halls, the upper balconies have like really nice residence properties because of tall ceilings and whatnot. I got the cheap seats, and their sound cloud is so low with so much space above. I think that's what was going on. But there's so much space above the sound cloud, and it was so low, and the orchestra was on the other side of the sound cloud. It was almost the music was almost unintelligible because I was getting so much reverb, not even reverb, like a second soundtrack almost of the of especially the cellos coming over the sound cloud and behind at like over a second delay at some points. Well, maybe half a second, but still, to the point where it's distracting. I thought it was an interesting story.
Yeah, I know. I'm not a fan of variable acoustics in a concert hall, where they have a room for the space that they open up for certain types of music. I'm not a fan of that.
Yeah.
Build it right, but one way, just let it go. Some things don't belong in the same space. For example, in Heinz Hall, which I think has great acoustics for orchestra, is not great for hip hop because it's just a little too reverberant, and the sound guys don't know what they're doing with a very different genre of music. In Heinz Hall, the cheapest seats are the best ones. Okay, I only have one other thing, John. I don't know if when you were in my class, whether I told you about this incident in San Marco and Venice.
I don't know if you did.
Did I ever mention that in class when you were there?
I can't remember.
But I think it was in the 1500s, the Doge of Venice he was way overweight, and he couldn't make it to the seat that was reserved for him in San Marco in Venice, this famous church, where Vivaldi and others had written music especially for that space. And so he told the acousticians that they had to change the acoustics to the seat where he wanted to sit, and they did it for him.
That's impressive.
John, that place in Epidaurus, I've been there, and they do
Oh, really?
Demonstration. They drop a coin in the middle, and you go sit at the farthest thing, and you can actually hear the coin.
That's awesome. I want to do that.
But I'm not sure they knew what they were doing.
Yeah,
Those
might have
Greeks,
been a happy
Greeks lie a
accident.
lot. I'm
Yeah,
Greek,
for
so I
sure.
don't trust them.
There you go.
Beware of Greeks.
Is that close to Athens? Is it close to big
No,
city?
it's south of that. It's in near Mycenae or something.
Oh, okay.
I
Cool.
think it's southeast or southwest.
Very nice.
It's an impressive though
Definitely.
demonstration.
Yeah, I'm sure. That's awesome.
Okay, John, well, thank you very much for doing this today.
Of course. Thanks for having me.
Will be when
Yeah.
we come in and do the second analysis of the Blahanka live room.
Yeah, I'll be in Pittsburgh definitely a few times this semester. So I'll send you an email and I'll come in and finish those up for you. I'm looking forward to see the results.
That'd be really interesting.
Yeah, definitely.
All right, thank you again. And
Awesome. Thank you. Great to see you guys.
You too.
Yeah.
Thank you.
Have a good one.